All right, so today we're going to talk about PCA. If either of you have any questions, feel free to just like interrupt me whenever. So the main things we're going to talk about are first unsupervised learning, because this is the first time we're dealing with unsupervised learning, and what exactly is PCA. We're going to talk about why we use PCA, how does PCA work, and how you're going to evaluate PCA. So a lot of text on the slide, but we're just going to go through it. Unsupervised learning. So all of Mod 3 was all supervised learning. And the thing with supervised learning is that anything with labeled data that we're trying to predict their labels, that's supervised learning. So unsupervised learning, which is what we're going to be doing actually this week, and I believe your next study group will be on clustering, is also unsupervised learning. And in unsupervised learning, what makes it different from supervised learning is that there are no labels. So I think it's easier to explain in the context of clustering, which we'll talk about, I think, either tomorrow or next week. But in clustering, imagine, and the most common example used for clustering is, imagine you have, all these basketball players. And I don't know sports too well, but from what I've heard sports people say, that in basketball, there are these positions that exist. But the way that the game has slowly changed and evolved over the years, these positions don't exactly group the players in the best way. And so a very common clustering project is to regroup these basketball players based on their features, like based on, I don't know, their like points scored per game, their like, I don't know, all their stats and their ratios. And maybe through this clustering, you can form, I think, I don't know how many positions there are currently in basketball, but maybe you can split them up into 3 completely different groups than what exists now. And what makes it unsupervised is that we're not telling the model how to group these people. It's based on different rules in the algorithm. So just to briefly talk about clustering is that you can tell the algorithm to just look at which points are closer together mathematically, like based on their numbers in space, which ones are close together, and group those together. And so these are unlabeled machine learning tasks because we don't tell it. The only thing we're telling it is how many clusters to do. So it's not labeled. And then once you've clustered these groups, then maybe you'll look into them and say, all right, yeah, these are the players that, I don't know, mostly shoot. And these are the players that mostly defend. And maybe you get a different form of grouping than what currently exists. So that's an example of clustering, which is an example of an unsupervised learning problem. So the next thing we're going to talk about is another type of unsupervised learning, which is the main topic of today's study group, is PCA. So PCA, I should have put it somewhere here, but it stands for Principal Component Analysis. And it's a form of dimensionality reduction. And so dimensionality reduction is this whole group of algorithms that, imagine you have a lot of dimensions in your data set and you want to reduce those dimensions. PCA is one of the most common ones. Another one, if anyone's interested, is called TSNE, spelled T-S-N-E. I forget what it stands for off the top of my head, but that is another very common one. But in our curriculum, PCA is the main one we're going to use. And so PCA is unsupervised because let's imagine we have this data set with like 200 features, 200 columns. It's unsupervised because the only thing we're telling it to do is to tell it how many dimensions to reduce to. So imagine you start your data set with like, how many did I say? 200 columns? 200 columns, and you're like, all right, this is way too many columns. One very common use of PCA is I want to plot my data onto a 2D graph. So I'll use PCA to bring down the dimensionality of my data set from 200 columns to just 2 columns so I can plot it in a scatter plot. That's actually a pretty common use of PCA. It's actually a very, very useful EDA tool. So the main gist of PCA is it reduces the dimensionality of a feature set into n principal components, however many you want, while maintaining its variance. So maintaining its variance basically means that, let's say you have every column, you have some form of variance. And the variance is actually what tells you it gives you quite a bit of information on like the spread of that column, on like, on maybe, let's say you have a few different classes of data, and the variance in each of those classes of data can tell you quite a bit about your data set, if that made sense. I feel like I strung a lot of sentences together. But the main thing you want to do is you want to maintain the variance. You don't want to reduce your dimensionality and everything just clumps into one big clump, because that is not helpful. You want to maintain variance, and I'll talk a little bit more about that later. And then the other thing to remember is that each principal component, so basically after you reduce the dimensionality, let's say you want to reduce it into 2 dimensions, each of those dimensions is called a principal component. So usually you'll see on a PCA graph, you'll have PC1 and then PC2, which are the 2 principal components that you've lowered down your dimensionality to. And each principal component is a linear combination of all your original features. So principal component 1 can be made of like 1/4 of feature 1, and then maybe 0.1% of feature 2, and maybe like 0.3% of like feature 3. And that's what each principal component is made of. So each principal component is made out of a linear combination of all the original features. Any questions about that? I feel like I just threw a lot of information. But cool. I think that the Learn Labs explain a little bit in depth. I mean, it's really in depth. It can be a little bit hard to understand because of all the math things. But I think if I will also send out a bunch of resources right after this Slack channel, which are some like really good videos that I think explain PCA really, really well. So, all right. Why and when do we use PCA? So as I mentioned, it's really to reduce your dimensionality. There's something called the curse of dimensionality, and I think a couple of our labs are actually titled the curse of dimensionality, and that's actually a very common phrase. So as the number of features increase, your data points become more sparse and far away from each other. And you can imagine in like this day and age, that actually happens quite a lot. Like imagine like Facebook. When Facebook first started, what data were they collecting? They were collecting data on like the things that we post, maybe our personal information that we put on there, but as they grow and as they like build their capability to collect data, they're collecting so many more columns now. And so imagine you find Facebook's data set and you want to do something with it. They could have like thousands of columns on one person. And so you would use PCA to whittle that down, because with more features, you have to deal with the difficulty of implementing these machine learning models. So imagine, like, I don't know how many of you've already done your Mod 3 project. Some of these models did take quite some time to run, right? And the more dimensions you have, the more columns you have, the more graded descent each algorithm is doing, the more work each algorithm is doing to optimize. So you really, to save time and to save on algorithmic complexity, you're gonna want to reduce your dimensionality. And when you think about complexity, not just time complexity, which is the amount of time your algorithm takes to run and train, but also space complexity. Because sometimes, like, if you're storing more data, if you have like your rows are always increasing, but if your columns are also always increasing, you're going to run out of space, and you want to be more efficient with that. So there are some data sets out there that actually store their data in principal components just because it makes more sense. And all you have to have is the transformation, like the linear combination of each principal component, and you can translate that back into your data. Does that make sense? Cool. And so when exactly to use PCA, it's when you have a lot of continuous features. So it doesn't work, it can work, but not as well on categorical features. So you want to see, like, I would say maybe at least more than half of your features should be continuous to use PCA. PCA is best for when you're doing something like clustering, because clustering actually looks at distance between points. We'll talk about that at your next study group. Or computationally heavy machine learning algorithms like SVM. So SVM is actually where I learned to use PCA, because SVM, I don't know if any of you tried that for your Mod 3 project. If you have a big data set with a lot of, the more columns you have, the longer SVM takes. And so it's actually very common to always do PCA before you do SVM. One more example that I actually didn't put on this slide is when you're dealing with text data. And so in this mod, I think 2 weeks from now, you'll be doing NLP. And with NLP, natural language processing, you're gonna have a lot of dimensions because every word becomes a single dimension. And so it makes a lot of sense to do PCA on that data set as well. Just so like, because if you have, I think I've worked with like data sets that have like maybe 10,000 unique words, and that is basically 10,000 columns. And so you will want to whittle that down to maybe even from 10,000 to like 50 columns is already so much better than 10,000. So you might want to do something like that when you get to your NLP project. Cool. So how exactly does PCA work? The way it actually works, you actually have to go into quite a bit of linear algebra theory. And so it is kind of complicated, I think, especially if you don't know linear algebra, but it's completely fine. I don't think it's important for you to understand like the true math behind PCA. So there is a lab actually that has you code out PCA from scratch. I'd say it depends on the way that you learn, whether that is helpful for you or not. Honestly, like if just implementing these equations into code doesn't help you at all, honestly, I feel like it's not the best use of time. But I'll just like quickly briefly go over. PCA works by doing eigendecomposition. And if eigendecomposition doesn't really mean anything to you right now, that's like a sign that like don't worry about it, you know? You definitely don't have to fully understand the math behind it to actually implement it. I think what's more important is to understand the concepts, which I'll reiterate later on. But these are the main steps. You have to first recenter your data. So the mean for each feature is 0. And so that, imagine like if you have a big clump floating somewhere in like your space, it recenters to 0. You want to find the covariance of that. And it sort of like calls back to, because I mentioned that PCA tries to maintain the variance of your data. So you're actually taking the covariance matrix, which is the matrix that looks at the correlation between each feature with every other feature. And then you're gonna get the eigenvectors, sort them, and multiply them by your data. So if that doesn't mean anything, the labs actually explain it with like a step-by-step where you code it out as well. That may or may not help. But I don't think it's worth going into too much. The videos that I'll send out later have like really cool clip arts of how that actually works and how it goes from like many dimensions to different dimensions. So I'll send those out right after this. This is my last slide, and it's evaluating PCA. And so the thing I mentioned at the start was how the only thing that you tell PCA is how many dimensions you want to lower it down to. And so it kind of depends on what your purpose for doing PCA is. One, I mentioned like if you're doing an EDA where you just want to visualize your data, you want to visualize your like 100 dimension data, you can PCA it down to 2 or 3 dimensions or 2 or 3 principal components, and that's easy to plot on a graph. You can plot it on a 2D or 3D graph. So that's done. The other thing, if you're using PCA to actually reduce the dimensionality of your data set to put into a model, this would be something that you would end up plotting. How many principal components is best for your data set? This graph is not labeled, but I pulled it from one of the labs. This graph is an explained variance graph. And so what it has here is on the y-axis, it's the percentage variance from 0 to 1 that percentage variance of the original variance. And I'll go into that. I think it'll make more sense as I explain it. And on the x-axis is the number of components. So preferably, you want to maintain as much variance as possible. So you take a look here at 10 principal components. You have maybe about like 75% of your variance there. So that means while doing PCA, you lost about 25% of your variance in your data. And that could maybe cause problems in like, you don't get as much nuance in your modeling. And so when you're doing PCA and you plot a graph like this, it really depends on like how big your data set is and like how much complexity you're willing to like, how many features you're willing to give up. But usually you want to try and strive for about like 90%. So I think this data set probably has about 60 features. And I'd say it looks like 90% is around like 30 features. So in this case, we would do PCA, knock it down to 30 features, and you still have 90% of your explained variance. And in that case, I would think that, all right, based on this, and it also does depend on your specific project, but in this case, I would, based on this graph, say, all right, 30 seems like a good number of principal components to go with. So it really does depend on your product. Sometimes these curves look a little bit different, but they do tend to taper off to 1 as you get to more and more features. So it does depend on how much of the variance you're willing to give up. Like I would say, if you have a lot of nuances in each of your features, you maybe want to like get it even closer to 1. But if you find that, all right, maybe, and there are cases where most of the variance can be explained in like literally 5 features. So it does depend on your data set. Everybody's graph will not look exactly like this, but I will say like, and I think the labs also say you want to get like around 90 to 95 of your explained variance, and that's like a safe amount because you're not losing too much information. So this is my last slide. The one thing I just wanted to reiterate was what PCA is, just because if you use PCA in any of your projects in the future and you put it on your resume, be prepared to explain what it is. And like a quick 1-sentence summary of what PCA is that it, let's see, do I have it here? Here, all right. So PCA reduces the dimensionality of feature set into principal components while maintaining variance. And each principal component is a linear combination of the original features. So that's just like the main takeaway. I think like if you don't want to get into the math, understanding what those 2 points mean are more important. But cool. Does anyone have any questions?
So is PCA, you were saying like Facebook as an example, is that like the real world type of scenario where PCA might be used?
So I honestly don't know what Facebook does, but if I chanced upon a Facebook data set and let's say I wanted to like, I don't know, classify users, I would use PCA to reduce the dimensionality because I would imagine that Facebook collects so much data on us people that I don't want to work with, I don't want to plug in like thousands of features into a machine learning model, you know? So it's really just for, it's really for efficiency. That I would use PCA to reduce the dimensionality of like Facebook's data. Whether they do it in real life or not, I'm not too sure.
Right, sure.
Another, oh yeah, go ahead.
Sorry, I was gonna go ahead.
I was just gonna say another like real life example is in images, in image data, because when you're looking at images, each pixel is a feature, is actually a feature. And so it's actually one of the I think the last few labs on PCA actually talk about PCA with images. Yeah.
Okay. And then so PCA is a starting point for a lot of projects, just to first narrow that dimensionality down.
I think it actually can come in at different points. So I personally like to use PCA to just, if I was doing a classification project, like a Mod 3 project, and my data set has like maybe 10 features, I would still use PCA to just lower the dimensionality to just see where they plot in 2D space. So you can sort of see like, actually I might have an example that I can pull up. But yeah, I would actually plot my, sorry, let me pull up one of my projects and I can show an example of how I use PCA. So I'm gonna share one of my projects, which was an NLP project. So actually I had, I think about 5,000 unique words here. And I just wanted to see, you know, what does it just look like? I know you can't really visualize like 5,000 dimensions, but this sort of helps. So in this graph, you can see I did PCA on 2 classes. And for a little bit of context, I'm just classifying text posts, whether they're about art or talking about programming. And here you can see after doing the PCA, there's a little bit of separation here. You can sort of see that like the blue ones are all a little bit higher than the red points. I hope that y'all can see this. Let me zoom in a little bit. Yeah, so this was just my EDA process. So after doing PCA, you can sort of see that like, all right, maybe the ones separate are not as clear, but in this example, you can sort of see how the different classes, all their features combined, because each of these principal components is a linear combination of all the features in the feature set. This is what they look like. Because I took this down from like 5,000 to 2, they still kind of come together. But at least I think it's still pretty telling that you can still see that like there are some parts that are strictly red and some parts that are strictly blue. But yeah, and you can also do this in 3D as well. This is just a 3D example. But yeah, this is an example of using PCA in your EDA process. So it can come in EDA, it can come in your modeling process just to let your models run more efficiently, faster. And yeah, I think those are the two main uses of PCA.
Thank you.
Of course. Anything else? Cool. Well, the labs on PCA I think they're very, very in-depth. I'm right when this video finishes processing, I'll post this video along with some resources that will go well. And yeah, any other questions, feel free to let me know. So yeah, that's all that I have for y'all today. Feel free to Slack me if there's anything. And yeah, I'll see y'all next time. I think for the upcoming study groups for your cohort, it's going to be a combination of myself and Jeff that are doing your study groups. And so the schedule might be a little bit off, but we'll like keep communication open in the Slack channel for sure. All right, in that case, have a good rest of your day, everybody, and I'll talk to y'all soon.
Thank you.